Welcome back to Further Maths in an Empty Classroom with me, Mr. Southern. This is part 2 of the video on vector geometry, and this example here just has a quirky little finishing touch to it. So here we go then. Refer to a fixed origin O. The points A and B have position vectors I plus 8j minus 6k and 3i plus 5j minus 5k respectively. And we're being asked to do a number of things here. We've got to find the equation of the line AB. Show that the point C lies on AB, show that OC is perpendicular to AB, and then the last little bit, we've got to find another point D. So I'm just going to break this down into the first two parts, which I'll just do on this slide here. So here we go then. We're given 2 points A and B. Now, as before, my preference is to write these in column form. So the first thing I'm going to do is say that vector A is 1, 8, negative 6, written in a column, and that vector B is 3, 5, negative 5. And then look at what we're being asked to do. We're being asked to find an equation of the line AB, which means I'm going to need the vector A to B because that is going to serve as my direction vector. So 3, 5, negative 5 minus 1, 8, negative 6 comes out as 2, negative 3, positive 1. Just careful with your signs on that one. So that is the direction vector of the line. So to turn that into equation, I just need to use either of the points that I know. I'm going to use the point A, 1, 8, negative 6, plus a multiplier, a parameter lambda, and then the direction vector 2, negative 3, 1. And that is the equation required in part A. Okay, part B, we're going to show that the point C, which has position vector 5, 2, negative 4, lies on that line. So just in the previous example, I need to show that there's a consistent value of lambda here that would work. And just for the sake of variety, I'm actually going to show this a slightly different way. So 1, 8, negative 6 plus lambda 2, negative 3, 1 would have to equal that point there, 5, 2, negative 4. Now, what I'm going to do is I'm going to subtract this position vector here, 1, 8, negative 6, from 5, 2, negative 4, and leave the lambda multiplied by the direction vector where it is. So looking at the I components, 5 take away 1 is going to be 4, 2 take away 8 is going to be negative 6, and negative 4 take away negative 6 is going to be positive 2. Now doing it this way, we can see that lambda is going to be equal to 2, and that is going to be consistent for x, y, and z. Therefore, C must lie on the line AB. So an alternative way of approaching it than setting up 3 separate equations, it's essentially the same maths. Now, if in part A I'd used the point B instead of the point A, this would still have worked. I would just have got a different value of lambda. So it doesn't matter which of those 2 points you use initially. Right, now moving on. So part C, we have to show that OC is perpendicular to AB. So I'm just going to jot down that we had that the vector equation of the line through A to B was R equals 1, 8, negative 6. Plus lambda 2, 3, negative 1. Just check, note 2, negative 3, 1. Let's just cheekily change that. There we go. And the point C was 5, 2, negative 4. So let's just jot that down here before we carry on with it. Okay, so we need to show that OC is perpendicular to AB. Right, so let's just draw a little diagram here. So we've got the line here, which is the line AB. We've shown in the previous question that C lies on the point, lies on the line AB. So what we're now looking to do is draw a line in from the origin O and show that that is perpendicular. Now, the way that we're going to do that is we need to show that O to C dotted with A to B equals 0, because if the dot product between two vectors is 0, then they are perpendicular. Now for O to C, I can use the vector C because that is relative to the origin O. And for the line AB, I need to use the direction vector. So crucially, I've got to use 2, -3, 1 rather than the position vector. And if I do the dot product of those there, I can see that I'm going to get 10 minus 6 minus 4, which is 0. Therefore, those two vectors are perpendicular to each other there. So that's part C. Now, part D. The position vector of the point D, where D does not equal A, such that O to D is equal to O to A. Now, let's just do another quick diagram here. We've got this point A here, this point C, relative to an origin, and we now know that that passes at right angles. So I'm just going to draw a line in A to D. Oh, sorry, O to A. And then I'm going to draw O to D. Now, if O to A is the same distance as O to D, and D lies on the line, then what I must have created is an isosceles triangle, where this point D is here. Now, if O to A is the same as O to D, it follows that A to C must also be the same as C to D. So if I note down the position vector of A, which is 1, 8, -6, and the position vector of C, which is 5, 2, -4, whatever translation I've done to get from A to C, I simply need to do again to get from C to D, because these two distances here are going to be equal as well. So let's look at what's happened to the I component, the X coordinate. I've added 4, so that means the D1 must be 9. With the Y, the J component, I've gone from 8 to 2, so subtracting 6 takes me to -4. And with the K component, -6 to -4 is adding 2, so that takes me to -2. So the position vector of D is equal to 9I minus 4J minus 2K. So again, as in the previous example, we see the power of a good diagram to interpret what the question is asking us to do. Thank you for listening.